In this video, the learner will apply and use the Hinge theorem to make comparisons in two triangles. What we've done so far is just compared sides and angles in a single triangle to one another to see which side was largest and which angle was largest. Now we're actually going to compare one triangle to another triangle. First, I just want to remember the side angle side congruence postulate. If you remember, that says if two sides and the included angle are congruent to two sides and the included angle of another triangle, that automatically means that those triangles are congruent to one another. Once I know the triangles are congruent, I know all sides and all angles are equal. Well, that must beg the question, what happens if the included angles were no longer congruent to one another? Say this angle E was bigger or smaller than angle A. But say the sides were still congruent. What would happen? Well, we would actually have this situation where we have our congruent sides still, but when we have a smaller angle, that's going to correspond to a smaller side opposite from it. Or if I have a larger angle, it's going to correspond to a larger side. And you can see this animation here where we have a rubber band connected to two sticks. And this right here is a hinge, like a hinge on a door that allows it to open and close. As we widen that angle, the rubber band is stretched farther and farther. As we lower that angle, points A and B become closer together, and the rubber band is shorter. This is what introduces us to the Hinge theorem. If two sides of one triangle are congruent to two sides of another triangle, and the included angle of the first triangle is larger, that means that the side that corresponds with it is going to be larger as well. So in these two triangles here, we know AB is congruent to FG. We can see that by the markings. AC is congruent to FH. Again, those markings with the two dashes. And we also know that the measure of angle A, which is 43, is greater than the measure of angle F, which is 30. Therefore, the measure of BC has to be greater than the measure of GH by the Hinge theorem. We also have the converse of the Hinge theorem, which says if we know two sides are congruent to two sides of another triangle, and the third side is longer, then we know the angle in the triangle with the longer side is going to be bigger. So if we knew that JL was congruent to PR, which we do from the diagram, and KL is congruent to QR by those markings, we can also see by the measurements that PQ, which is 12, is bigger than, or the measure is greater than, 8, which is the measure of JK. Because we know PQ is larger, we know the angle across from that, which is angle R, has a larger measure than angle L, which is across from 8. So notice in this first one, the Hinge theorem, we're talking about given that we have those two congruent sides first. No matter what, we have those two sets of congruent sides. If we have the angles in comparison, then we can prove something about the sides. In the converse, given that we have those two congruent pairs, if we know something about the sides, then we can prove something about the angles. So know which one to use, whether we're using the Hinge theorem or the converse of the Hinge theorem. All right, in these two examples, notice I'm given that WZ is congruent to ZY. I want to compare WX to XY. I can also see that XZ is going to be congruent to itself by that reflexive property. So I have that given criteria that I needed, those two sets of congruent sides. I also see that angle Z is bigger than angle Z in the other triangle. So angle YZX is 55, angle WZX is 51. I know the side across from the bigger angle is going to be larger. Therefore, I know that XY is the longer side, so WX has to be less than XY. Notice I'm using the Hinge theorem because I was talking about angles first, and then I'm proving something about the sides. In part B here, I want to know something about angles. So if I'm wanting to know something about angle comparisons, I know I'm probably going to be using the converse of the Hinge theorem. I can see here in the two triangles that BF is congruent to CD, and CF is congruent to itself by the reflexive property. So I have the conditions that I need to have to try and use the Hinge theorem. I have those two sets of congruent sides. Now I need to know how to compare angle FCD, which is across from the measurement of 3, and angle BFC, which is across from the 3.6. I know the bigger angle is going to be across from the longer side. Therefore, I know angle F in this triangle, BFC, has to be larger than angle FCD. So BFC has to be greater than DCF by the converse of the Hinge theorem. In these two examples, I want you to try these on your own. So if you'll go ahead and pause and copy those down. Next, I have another application of the Hinge theorem. I want to find the possible range values for the value of x. In these triangles, I see EH is going to be congruent to itself by the reflexive property. JH and HG are congruent segments by the markings in the diagram. So I know I'm given two sets of congruent sides for the triangles. Therefore, I know I can use the Hinge theorem. And possibly its converse. I notice also that I'm given side lengths, and I have a measurement of 65 for angle EHG and an expression representing the measure of angle JHE. So from the picture here, I'm given side lengths of 11 and 9. 11 is greater than 9, therefore the angle across from the 11 has to be larger than the angle across from the 9. So because of that given information, our two sets of congruent sides and our third set of sides where one is bigger than the other, I know by the converse of the Hinge theorem that angle JHE is bigger than EHG. Now I can plug in and substitute the expression for JHE and 65 for EHG, and then solve that inequality. So subtract 15 and divide by 6. So I know the value for x has to be bigger than 8 1/3. Well, just that inequality implies that it's everything bigger than 8 1/3. But we know in a triangle that angles can't be greater than 180 degrees because angles in a triangle add up to 180. So I have to consider the inequality where 6x plus 15 is less than 180 because this angle, JHE, has to be less than 180 degrees. Then I solve that inequality and I notice that x has to be less than 27.5. So I have two boundaries here. X has to be bigger than 8 1/3, but smaller than 27.5. And I can write it as a compound inequality in this format or in two separate inequalities. Both are acceptable answers. And here's an example that I want you to try on finding the range values for x. Notice that 5x plus 2 is a side length in this triangle.